All right. So what is resistive random access memory? How many of you remember STM RAM? We had a storage element called magnetic tunnel junction, right? And depending on the relative magnetization, it used to give us two levels of resistance. Actually, yes, current, true, but the reason why we had two different levels of current was because we used to get two different levels of resistance, right? So using two resistance levels to represent 1 and 0 is not a new thing for us. Who else can give me a different example of that? Which other memory element used two different resistance levels? Should remember this. Well, yes, the easiest example would be phase change memory, don't you think? Amorphous, high resistance, crystalline, low resistance. So we basically utilized resistance differences to represent data already. So why all of a sudden we have a different lecture on this, right? Well, the reason is those memories, despite using resistances, they relied on a different physical phenomena. First, spintronics, that's for STM RAM or magnetic tunnel junction, and crystal structure, heat-driven crystal structure reorientation for phase change memory. It's a very different physical mechanism. But turns out there is a different class of devices, different class of materials that leads to resistance changes due to other physical phenomena that can also be used as a memory. And they typically come with some additional features that phase change memory and STM RAM don't have or don't require. And I hope you'll appreciate that once we go through the entire lecture, okay? So it's similar to, you know where we're going with it. We'll have two resistance levels somehow in a material, and we'll represent 1 and 0 with them. That's all. Okay? All right. So this chart came back, which I kind of skipped during PCM lecture. I also skipped during FFED because I wanted to cover it along with everything else that we cover, right? So that we don't go over the same chart multiple times. So I'm skipping it one more time today, but I will get back to it after we get done with RAM as well as the crossbar RAM later on. Okay, so get back to this chart. It's there for you to, whenever you're reviewing these lectures, if you want to just quickly take a look at it, is it good or bad? Is it good in terms of speed? Is it good in terms of area? We could quickly go back to the chart and take a look. But let's start with the basics. The first term that I wanted to pitch is memristor or memristive memory. What is a memristor? Basically, it comes from two words, memory and resistor. A resistor that has a memory. So imagine if a device could have two resistance levels, 10 kilo ohm and 1 mega ohm. And it could remember that it was programmed, it can be programmed into two different states. And it could remember that, hey, I was programmed to 1 mega ohm. So I'll remain at 1 mega ohm. Or vice versa. You see the point? If a resistor had a memory, that would be a memristor. That's exactly how the name comes. A resistor with a memory. Okay. And what do we mean by that? Let's take a look at this simple current voltage characteristics. And that's where things begin. Follow along as I draw. I will be drawing on top of this curve. Okay. Hopefully it will feel easier if you follow along this description. So at 0 volt, this material could be at any resistance levels, but we are assuming that it was at a higher resistance level, high. So basically, as you increase the voltage across it, the current through the material increases. Right? You see that? Voltage increases, current increases. Simple. At one critical level, you have an abrupt change in resistance. The resistance suddenly decreases. How do I know that the resistance decreased here? Because the current went up. If the resistance reduces, current will go up, right? So you see as abrupt change in current. That means at this stage, the material transitioned from high resistance to low resistance state. Okay. And now you decide to just let it go. You make it 0 volt. All on a sudden, you take off the applied voltage. What does the material do? So basically, well, it turns off, of course. When you apply 0 volt, it goes back to this point again. 0 goes back to this point again. But when you restart, when you start, like, okay, now I'm ready to provide voltage again, 0.7 volt. Now it no longer starts from this route. It starts from this curve because it remembers that, hey, I was programmed into low resistance state. I should behave like a low resistance state. Make sense? So now it follows this curve. And no matter how many times you keep repeating this voltage, it always follows this curve. How can you take it back to the high resistance state? For that, you have to apply a voltage with opposite polarity. Similar to, you see, it's almost similar to ferroelectric capacitor, don't you think? But that was a capacitor, not a resistor. And there is polarization, not resistance, right? Similar, but there are enough, dissimilarity. Okay, so when you apply a negative polarity, what happens then? Can you tell me which line it will follow, A or B? Initially, A, thank you, because it is in low resistance state. So it will follow the low resistance path first until you reach a section where it basically changes itself into high resistance state, like this. And then if you let it go, it will get stuck at 0 again. But then when you restart, it will start like this. No matter which direction you apply the voltage now, here or there, it will follow the high resistance curve until you cross over this threshold again. So there are two thresholds. One called the set voltage. We typically represent set when you go from high resistance to low resistance. And we mentioned the other one as reset, when you go from low resistance to high resistance. So there is another V reset. Yes. Yeah, so that's a great question. First of all, to switch from high to low, you have one definite polarity. It's always positive. Once you switch to low resistance, as long as you keep applying the same polarity over and over again, it will never switch back. Okay? If you apply a negative voltage as well, it will still follow low resistance until you exceed the threshold on the other side. Okay? So there are two thresholds in both sides. If you are not using the relevant threshold, it will never switch. Okay? It will only. Does it sound like some other device that we saw before? There was a device that will only flip if you flow current in one direction versus the other. Which one was that? Magnetic tunnel junction. Remember? You needed to flow current from one direction or the other to have anti-parallel to parallel versus parallel to anti-parallel switching. Exactly the same. See that? But completely different physical mechanism. And you're not dealing with spintronics here. You're not dealing with electrons tunneling here. All sorts, but phenomenologically, there are many symmetry. Does that make sense, folks? Okay. So do you now understand this IV characteristics? This is known as the famous butterfly curve. Like it looks like two wings of butterfly, if you think about it, right? Okay. So this is the signature of a memristor. This is the signature of a memristor, a resistor that remembers, has a memory. Okay. All right. I'll tell you why it does what it does, but I just started with what it does. But we'll now talk about why it does what it does. But before I do so, I want to be a little bit more realistic. This is what most papers or most sources will present. What they don't present is the figure here. What changed? See, it nicely marks set and reset. It shows with arrows where things are going, blah, blah, blah. But it has one extra information. What is that? Well, thank you. Thank you for pointing it out. But these are different devices, so don't take the numbers too seriously. And these are taken from two different sources. So don't take the numbers too seriously, but just look at the phenomenological changes. You're switching from high resistance to low and blah, blah, blah. All good, except for one thing, which is new. Can you see this one? There is an extra line, and I marked it as forming, and then nothing happens here. Why is that? So remember, forming is a procedure that takes place just once in the lifetime of a memristor. just once. And then you could use it millions and billions of times, but you just do it once. It's kind of like, seasoning a new cast iron. I don't know if you guys cook or not. You just have to do it once, right? Something similar, something that you just initialize once and then you don't have to worry about it again. So forming, well, who cares? I mean, just ignore it. But towards the end of this lecture, I'll show you this is one of the biggest disadvantages of resistive memory. Okay, this is one of the showstoppers. So funny how easily we could ignore something that has so much impact. I don't know if you have noticed or picked up this theme. Every time I talk about a new technology, I talk about the good things. It feels like, oh, this is it. Oh, wow, we found our solution. But then there comes challenges and you see, oh, no, it's not going to work. So that's the reason why we don't have a solution that replaces SRAM or DRAM at this point. Okay, anyways, I'll get back to what forming is after a few slides. Okay, I'll explain why forming is a problem and what this thing really is. Okay, so what is this illustration representing? This represents one class of memristor and one possible physical reason why this type of switching could occur. That is called filament formation. So imagine you have a metal electrode on the top, you have a metal electrode at the bottom, and in between you have some sort of oxide or insulator. Okay, typically oxide. There could be others as well, but typically oxide. And if you could somehow create a bridge, a conducting bridge, imagine a metallic bridge or something through which electrons could flow, then you have low resistance. But if the bridge is broken, then you have high resistance. Does that make sense? Well, since the illustration is here, I can easily use it to explain forming, by the way. Imagine if there was no bridge at all, like nothing. There is no concept of a bridge. You just have an electrode at the top and bottom, and you have an oxide in between. This is called a pristine material. It has never been used. Make sense? Okay, so if that is the case, when you try to create the bridge the first time, it's going to be difficult because to pile up all these elements, and I haven't told you what these elements are, that comes in the next slide here. Okay, we'll talk about it in a second. But to bring all of these entities to form that bridge, it takes a lot of effort. That's why you need a high voltage, much higher than the set and reset. I mean, it can be even higher than that, what you see here, by the way. To just pile up enough resources to create the bridge the first time. But after you have created it the first time, when you break the bridge by, resetting, like, what did I do? Sorry. Give me 1 second. Let me just make sure. Screen is being shared. I guess PowerPoint crashed. We'll see. Screen 13. Okay. I mean, all right. So I was going to say, not again. Nervous now. Okay, I hope. All right. So bad apple. I don't know if you got it, but Apple. I blame it on Apple. But okay. So imagine, do you guys all agree that to create the bridge the first time, it's going to take more resources in terms of voltages and currents? That's why it takes so much, high voltage. But once you create it, yes. It's a very different phenomena, but it looks similar to the transistor pinch off and whatnot, but it has a very different phenomena. And I'll talk about it in a couple of slides, okay? But the point is, when you break it off, we don't just completely erase the filament, to nothing. We break it into a small section, this one only. And then when you remake it, you just have to make for the missing part. So that's why set and reset voltages are much smaller. You can keep resetting and setting with lower voltages. But forming for the first time, it takes a lot of voltage. Does it sound like a challenge to you or not? Okay, just one time, it's okay. Does that make sense? Like, okay, you pay a premium just to be a member. And then after you're a member, you just keep using it without, you don't have to renew your membership ever in your life. It sounds like a good deal, don't you think? But I'll tell you, in hardware, that's a bad deal. Even if it is a one-time thing, it could be a bad thing. And hopefully I'll get time to cover that today. If not, we'll see. Okay. So phenomenological comparison. I already alert to the fact as we were going through it, but just in a formal setting, this is what a memristor does. Please pay attention to this, okay? Why does it look different from what we saw here? Can anybody tell me? This was absolute value. So typically when you have negative voltage, your current flows in the other direction. So this should be flipped like this. Don't you think? But it's difficult to track. So we use absolute value to plot. And that's why all these curves have absolute value. And also, when you plot in log scale, you cannot have negative numbers. Okay, so it's a semi-log scale. That's the reason why it's plotted in the other direction. But practically, when you measure, you see current in positive direction and negative direction. Basically, the current direction changes. That's why it's negative. And also, this is in linear scale, not log. So that shows you. You change from high to low and then go back to 0 and then low to high, blah, blah, blah. Okay, the same argument applies here. LRS stands for low resistance state. HRS stands for high resistance state. You already know what set voltage is and reset voltage is. Okay. All right. Look at ferroelectric FER. There is some sort of similarity. You needed two polarities to switch from one memory state to the other, which is similar here as well. Spintronic memory, you needed two polarities, by the way, like changing polarity of the current. And that's where basically current was the main driving force, not voltage, by the way. We had to inject currents because we needed electrons to flow through. Okay. This is another more fancy. I mean, I just had it here in case we'll talk about it, hopefully at some point in the cryogenic memory lecture, by the way. It is a more fancy device as topological insulator. Okay. And based on the current level, critical current plus and minus, you switch from one resistance state to the other resistance state. And there you go. You have two resistance, R1 and R2 represent 0 and 1 with it. So basically cryogenic memories use some cryogenic fancy devices, but it's still the same concept. You need two levels at least to represent 0 and 1. Okay? The concept remains the same. Are you guys all good? Okay, since we touched upon it, why do we like it? Because this memory gives you absolutely zero variation. I mean, there is nothing else in the world like known to us as of yet in electronic materials and whatnot that gives you this feature of absolute zero variability in two resistance levels. Okay, think about a memristor. I tell you that you have a high resistance state, a low resistance state. Fine, sure, but it's not really two states. Did I tell you that there is never a number? There is always a distribution. Threshold voltage of a transistor, it's never 0.2 volt. 0.2 volt is just the mean. You have a distribution. Everything has a variation, except for this topological insulator, because the resistance levels are quantum mechanically protected. I'm not getting into the detail of it, but there are reasons why people would go for this fancy stuff, setting aside all these other conventional things, right? There are reasons. There has to be a selling point, and that's the selling point there. Okay, getting back to normalcy. Why it does what it does? Let me tell you. So typically, the structure requires two metal layers. One metal at the top, the other at the bottom. They could be the same metal. They could be different metals. People have been experimenting with all sorts of combination. Say silver everywhere, silver platinum, silver gold, copper, cobalt, you name it. They've been trying with different things. Okay, and in between you have oxides. Okay, you have oxides. So when you apply some sort of voltage, say positive voltage to the silver, it's possible that silver atoms will diffuse. So basically, quite literally, atoms diffuse. Since they are metallic atoms, they're conducting. Okay, so you basically take out a portion of this contacts and you create a bridge. So these contacts themselves provide the material for the bridge. Am I making sense at all? So basically imagine you have silver here, and silver has atoms, of course, silver atoms. When you apply positive voltage, you encourage the silvers to leave this layer and gradually diffuse towards the other direction. And if you could make silver do so, you create a conducting bridge. And then when you rupture, basically you apply opposite polarity, you basically invite all of the silvers to the other end. So some of them break free from this section. So you have a broken bridge. Yeah. Let me take a moment to fast forward and let me show you. Go back a few slides because this is taken from one of my papers. I have more data about this. This is exactly how it looks like atomistically. This is looking at the atoms, atomic structures. Take a look. The silver, this is how the silver atoms are organized. This is how the platinum atoms are organized. This is how the hafnium oxide looks like, atomistically. Okay. When you apply voltage, electric field being in this direction, silver atoms are lighter than platinum. Okay. So they feel the heat and they basically get kicked around. And these silver atoms gradually leave their mothership and move towards the platinum side. This is literally happening like in few nanoseconds, even sub-nanosecond, by the way. And they create a bridge, a random bridge. Remember the term, it's random. I mean, we don't have any, we cannot create a bridge in this direction. No, it's like random stochastic process. But there will be a bridge eventually. So these atoms will connect silver with platinum. And when you have a connection, just erase it here. When you have a connection, you have low resistance. When the connection is broken, you have high resistance. So that's a physical mechanism possible. Yeah, I will just go back to that slide again. All right. Does that make sense to you, folks? So you can read this, and there are different kinds of metals that people have tried using. Some of these are called active metals. Some are passive. Active ones are the ones that actually move around. Passive ones like platinum, they are so heavy that they just create a base. They don't move around. They're conductor, but they don't move around. Okay, only silver moves around. Yes. Yeah, that's a great question because that helps me add a perspective. Okay, the perspective is, how much gold is being used in our processors? There are some people who make a living out of, right? They just take your processors that you throw out and extract golds and other precious metal out of it. So they're being used for their electrical properties. So you need the best performance, okay? And by the way, remember, when you think about nanoscale, Professor Blaylock told me a really nice story. I don't know whether I should share it with, okay, maybe I'll paraphrase it without giving out the characters, okay? So he was having a discussion with someone, and that person was an environmentalist, like cares about environment. And they were talking to him about, hey, you are making all these chips and you are using all these materials, and at some point we'll run out of silicon from the world. So then the point is, these devices are so tiny. We have to think about nanoscale, right? I mean, you could just make entire factory work with, I don't know, few grams of platinum, for example, okay? Like really, really tiny amount, much less than you use for your engagement ring, for example, okay? So it's really, really, really small amount, a meager amount that we need to use in these systems, because nanometer is so tiny that we cannot even fathom. Okay? So you need very less amount of material. So Professor Blaylock basically told that person that we're never going to run out because we use this tiny fraction. But apparently, again, it's not sounding funny because I am paraphrasing it and I'm taking out the funny part here. Anyways, the point is, people often have a misconception that, hey, chip makers are taking up all the materials. They're gonna run out of silicon eventually. No, we need so small amount of most of these materials that we don't care. It's not the same for battery, by the way. For battery, you have a lot of material. But for chip making, chips are tiny, nanoscale. You don't really need that much material, okay? That's one. The other reason is, yes, it's just one example. silver and platinum. People have tried with all sorts of combinations that you can imagine. Turns out you just go with the ones that gives you the best performance. And you don't care about the supply because you need a tiny amount. So it's not expensive at all. And by the way, interestingly, I mean, do you guys know how much a washing machine costs? Like if you were to go and get one from, say, Costco or something, how much will it cost? Approximately $500-600. Okay, in ballpark, if you take something fancy, $1,000 max, but typically 500, right? It's true. I'm not making it up, am I? Okay. And you see how bulky these things are. Will you be able to just lift one by yourself? Probably not. Okay, so they're heavy. So they have a lot of material. Don't you think? They have metals, they have a lot of materials and other materials as well, not just metal. So why am I telling you this? How much does an iPhone cost? More than the double, at least. You could, okay, if you add extra memory, which is like this tiny of a chip, $100. Do you think that is $100 worth of material? Never. If that's the case, then this washing machine will cost a fortune compared to that, right? At least 1,000 times heavier, I think. Whatever. My point is, materials are not expensive, honestly. Our Earth has a lot of material. We don't realize it, but when you fly, just look down on the ground and see how tiny we are. Like, look at all those big cities, but they look tiny fractions. Like when you're flying. Basically, we have a lot of materials around us. Not everything is as abundant, but most of it is. But what's costly is what? Technology. You know, so the reason why you pay that much money for iPhones is not because of the material that they are using, not for aluminum. Basically, they are recycling the aluminum anyways. They should give it to us for free, and they are giving it to us for free, honestly. The material cost is zero. And we know that in chip industry, they don't really charge you for material at all. It's like almost free. Just take it for free. Pay us for the technology to shape them into a form that makes something useful. So you're basically shaping materials, but you're not charging for the materials. You're charging for the technology to shape it into something useful. Okay, all right. Sorry, I took a tangent, but did I answer your question? Okay, all right. So this is just an example, but one good example, because this is one of the better memristors out there. Okay, I'm gonna give you one more example here. Ready for it? It's a completely different kind. My intention here between this slide, this slide, this slide, and the other slide, the one that's coming up, okay, is to show you that diversity in memristor device structures. There are different kinds of physical phenomena that collectively give rise to this type of resistance switching. But they all come down to what? They all come down to this IV. Make sense? So this switching occurs for different reasons. It could be the metal bridge that you just saw. It could be other things that we will cover. But you don't care. As an engineer, you could just run with one of them. Okay? Why are people trying to design this with different physical phenomena? Because they're trying to see which one gives you best performance. Remember, we have to address a lot of things. First of all, how many times can you switch? Okay, one thing here is, notice, if I keep making and breaking this bridge, at some point, will the materials be fatigued? Will it just give up? Will it just stop working as well? That's one concern. Number two, how about variability? Did you see the atomistic result that I showed you? This is more realistic. And did you see the randomness? The atoms could move in any direction, scattering and whatnot. So you don't have really much control over the filament size and direction, right? And number. There could be multiple filaments, like 1, 2, or 3, or could be just one, right? Yes. It's a great question. Great question. Yes. So there is no such thing. Okay. So typically it's equally likely everywhere. That's why it's so stochastic. And people use this to make random number generators, by the way. Okay. But there is a strategy that people use. What is that? They try to make them as small as possible. 100 nanometer diameter versus 10 nanometer diameter. For 10 nanometer, you're more likely to just get one filament because it simply cannot fit more. So that reduces variability. But if you have a bigger dimension, then you can have randomly creating bridges everywhere. If you have 1 versus 2, imagine if you have one bridge, you have say 100K resistance. If you have 2 bridges, you have 50 kilo ohm resistance all on a sudden because you have 2 parallel paths. basically reducing your resistance by half. So how do you deal with this degree of variability? Okay, this is a concern. So let's think about a non-bridging architecture. Non-bridging, that doesn't really create bridge. One option is to go with this, to create an oxygen filament. So remember, in the previous strategy, we used the metal. This was metal, this was metal. Could be same metal, by the way. Even in my graduate school, I tried with symmetric metal, like silver as well, silver, platinum, and whatnot. Oh, I forgot to mention one more thing. That reminds me. Sorry, this set and reset voltages may not be the same. Maybe you have 0.3 volt set voltage, 0.7 volt reset. So they may not be the same. And typically they are not the same. Why? Because of the asymmetry in the metal, silver, platinum. In one direction, you have a type of metal, the other you have a different type. So they're typically not symmetric. So we were trying to make, because of our sponsors, we're trying to make them symmetric. And that's why we tried using silver in both sides and see whether we have something useful out of it, okay? So it's possible to make them as symmetric as, or somewhat symmetric, but usually they are not. Just keep that in mind. Are you surprised? I mean, that's the same thing we observed in magnetic tunnel junction. Remember, I told you that between anti-parallel to parallel and parallel to anti-parallel, one of them is more difficult to achieve than the other one. There is a concept of right asymmetry. Am I speaking to myself or are you still with me? All right, okay. So here we are changing the strategy. Instead of making the metal move around, let the metals rest. So we use a different kind of metal that don't just run around places. They're just stuck. Maybe both platinum or platinum and some other heavy metal, gold, for example, okay? They don't move around that much. So now you are making the oxygen work for you. So you have oxide in between. I told you, previously we were just using it as a medium. But now we'll be actively forming defects in oxides. Remember, there are defects in every structure, broken bonds in every structure. What you do is you align the defects like this. Oxygen vacancy, basically. Vacancy or defect, whatever you want to call it. You align them. When they're aligned and create a bridge, that's when electrons from metal can hop. Defects are basically broken bonds, for example. So broken bonds, we will either have more electrons or less electrons. Typically, they have less electrons, missing electrons. Okay. So when there is an electron missing, remember, missing electron, you have an electron sitting here. It can jump to the next missing electron spot, or the next one, and then get out. So this mechanism is called hopping. It's a known mechanism, okay? Transport mechanism. Yes. It is still an oxide layer, yes. Yes, but you're putting the oxide to work. Don't just sit there, work for us. Like, okay, we have had the metal work for us, but it didn't work out that well. Because it was too many variation, too stochastic. So let's make the oxide work for us. Yes. It's a great question again. I mean, I wish I could go down to that degree of detail, but that's a great question. The thing is, yes, that's what do you think material scientists are doing, right? They have to have a job, right? So that's why I tell you, this is a multi-dimensional effort, material, device, circuit, system, and architecture. If I give my stochastic device to a system designer or circuit designer, they will figure out a way to make it work, actually. Oh, you have stochasticity, don't worry. We have this mechanism, feedback mechanism that will make it useful. Okay, but now if I go back to my friend from material science, man, yes, my friend from circuit design told me that they can work with stochasticity, but I don't like it. Can you help me reduce it? And the idea that you suggested, yes, they will come up with fancy structures, meaning you have barrier layers and you just restrict the filament within one layer so that you have less variability. But remember, every time you are asking for additional complexity in the structure, that adds to the cost. You might think, how much will that layer cost? It's not the layer, it's the process, the fabrication process. When you make them, you basically send a silicon wafer, not just one, thousands of them. And they go through a machine to, to do one level of etching, one level of deposition, and things like that. Okay. So when you ask for an additional layer of material, that will dramatically increase the cost. Okay. So people have done it, they published it, but they're not really used in the mainstream because of the complexity in the fabrication. Okay, it's possible. Maybe at some point, if we become so desperate that we really need it, we cannot live without it, then they will go back and like phase change memory. It took 40 years for people to go back to phase change memory and reuse it, right? So it's possible. To answer your question, it's possible to do some interesting material structure engineering, and that's what people do. And they write papers, by the way. When they write papers, they don't think about the next product. They think about the knowledge. For example, somebody will ask this question, can this be done? Google it, you'll find the paper. Oh, these guys have already demonstrated it can be done. So that's what they're looking for. They're looking for sharing knowledge, not making a product. Does that make sense, folks? Okay. All right. And by the way, everything else is exactly the same. I'm not going to go through the entire thing. I already discussed what reset and set is. Looking from the top layer, you either break the filament or you create the filament. That's how you set and reset. Simple. But here the exception is the filament is not metallic atoms. It's oxygen vacuums mostly. All right. And by the way, there are benefits of this approach. It's typically fast switching. It has higher endurance. I wrote all of these things down. You don't have to memorize, but you can just read through it and let me know. And typically, it also gives you good retention, more than 10 years. So we like it. We like this type of memory. Okay. And by the way, just to add, this is an auxiliary side to previous one. I gave you one example of how electrons can flow. Hopping. Hopping is just one example. Okay. I don't know if it is mentioned here. Yeah, it's mentioned here. Nearest neighbor mention. Hopping. These are taken from papers, as you see, sources. Hopping is just one physical mechanism through which electrons can flow. But there are other mechanisms that could take place. I'm not going to go through this laundry list. You have seen direct tunneling before. Direct tunneling is the plain vanilla tunneling. Electrons, barrier, flow, go through the barrier. That's direct tunneling. We saw Fowler-Nordheim tunneling before through a triangular barrier, but you haven't seen possibly the other types of conduction mechanisms. It's not a physics course, so I'm not going through it. I want you to know that it's not the only thing. The hopping is not the only solution, okay? There are other mechanisms that could take place, but the point is electrons will go from here to there through this bridge. Does that make sense to you guys? Okay. I remember we had a paper on memristors. There, we at least consider 7 or 8 types of conduction mechanisms. Don't get me wrong. I'm not saying that in different devices, there will be different conduction mechanisms. There will be one prevalent characteristics like hopping that will lead to current conduction. But there are other secondary mechanisms. Maybe if you have 100 electrons, 10 of them will hop. 2 of them will directly tunnel. 1 of them will do Fowler-Nordheim tunneling and blah, blah, blah. You see the point? So electrons will find a way to go from A to B, but they will use different physical mechanisms to do so. Did I confuse you? So within the same material, same structure, you have multiple physical phenomena working simultaneously, not just hopping, not just direct tunneling, not just XYZ, but all of them or some of them working together to lead to a current. But see how easy our life is as an engineer? We don't care. Just go back to IV, right? IV. That's what we care about. But deeper down, if you're a material scientist or physicist trying to understand why it does what it does, sure. There is a laundry list. And these are the ones that we know of. I'm sure every 5-6 years, people come up with new mechanism. Oh, the new phenomena that gives rise to current. Okay. We just have 1 minute. So let me just finish this slide, okay? Give me like 1 more extra minute, please. I'll finish this slide and we'll have a nice place to start in the next lecture. Okay. So interfacial redox reaction is similar. So there, you don't really have any filament at all. Metals don't move around. Oxide don't create bridge. What happens is you have a redox reaction closer to the, basically a chemical process. You see that? We are using chemistry. You have a redox reaction right here. So through that reaction, you create a layer of material that leads to low resistance state. And if you have more reaction, it becomes a thicker layer. So just take a look at these 3 figures. Thinner, slightly thicker, even thicker. So it depends on how much reaction you have done. So the more it reacts, the more thicker the layer is. So apparently, this has resistance 1 resistance 2, resistance 3. So you can create different levels of resistances, not just low and high. Why is that useful? Did I talk about it before, folks? Multi-level resistance. If you keep doing so and maybe create one more, you have 2 bits stored per devices. So this is one more recent kind of memristors that are emerging. People are looking at it for multi-bit purposes specifically. And good thing is it doesn't have a filament. Bad thing is it is slower. Okay, just so you know, there is no clear winner, but it's out there. And by the way, I gave examples as well. Like, these are more fancier, as you see. Right? It is difficult to even pronounce. Some of these are more fancier. And all of these are recent, like 2020 is recent compared to the technology standard, if you think about it. Okay. All right. So I'll stop here. 3 different kinds that you learn. 2 uses filament. 1 uses filament from the metal. The other one is non-metallic oxide filament. The third one, no filament at all. Just react. Okay. Okay. So we will get back from this array architecture in the next class. Okay. Thank you all. I'll see you on Wednesday. Okay, please make sure to register as well. Submit your registration first. This is important because I have to share